We're here today in Orlando, Florida at Gamers Inc. To talk about this, the Xbox 360. But more importantly, we're here to talk about the components within inside, namely the GPU and CPU, as they have undergone what people like to call a horrid example of how to cool and mitigate your internal system. This is the inside of an Xbox 360. Right here is the DVD drive. We take it out. We see two sets of heat sinks, one for the CPU and one for the GPU. Right here is a fan duct. This mitigates the airflow from the CPU heatsink and the GPU heatsink. No other spots in the Xbox are accessible by a fan. Thus, the only way to go out of the Xbox is through the back. Xbox 360 motherboard. We have removed the heat sinks, as you can see. It's different from this. And it is exposed to us its internal components. Right here is the CPU. Right here is the GPU. And right here is different memory or RAM. Also on the bottom you can see the same thing. Right here under the GPU is different capacitors, resistors, and other electronic components that help power the GPU and make it perform the way it should within the Xbox 360. There is a similarity between the CPU and GPU, being that the CPU, the central processing unit, and the GPU, the graphics processing unit, each perform different tasks. If you look closely at the chips themselves, you see a reflective surface on the top. This right here is what passes the heat that radiates from every single task from each little atom inside each silicon transistor. If you take a closer look, which has been dramatized by breaking the top of it, we can see there's many layers to this transistor grouping. About 50 years ago, it would take a room full of vacuum tube computers to run a fraction of the processing power that exists today. The amount of processes performed, being billions under heavy load, create a substantial amount of heat. And unfortunately, we need to pull the heat away from the chip, or else it'll melt off, or worse, blow up. Thankfully, they've prevented that by just making the thing melt off before it blows up. Here we have a collection of heat sinks that are in different versions of the Xbox 360. Right here are the GPU heat sinks, this being the first version, and this being the later version. And right here, we have CPU heat sinks, this being the first, and this being the later. What these intend to do, take the heat away from the chip itself so that it can be displaced outside of the Xbox, so that the Xbox can function correctly. Now, if we look at the bottom of the heat sinks, we can see that they're all made of the same material, except for this one right here. This one would be copper, these being made out of aluminum. If you see the marks closely on here, you see that there's kind of a residue on here, actually looking like the top of this chip right here. This is because you actually need something to pass the heat from this chip to the heat sink, and then to the source that's going to take it away from the heat sink. So to make up for the lack of transfer, we use something that's this. This is thermal paste. Namely, this is Arctic Silver 5, which is a high-density polysynthetic silver thermal compound. The job that this does is so important to electronics and what we do here that without it, we wouldn't be able to do anything. What it does is it takes this chip, it fills it in the perfections on top of the reverse silicone. We apply a thin layer to it, and then we put the heatsink on top of it. What it does is every imperfection that we can't see, but exists there, it fills it, and it enables it to transfer the heat way better than any other type of thermal paste that's actually out there. So you might be asking yourself, why do I need to know any of this? Why do I need to know about CPUs, GPUs, heat sinks, thermal paste? Well, it all boils down to what's going on in the Xbox and why they're breaking is what's intriguing to us and why we strive to fix it and understand what's going on. If we look at the bottom of the GPU, we see what looks like a mess. Each one of these connecting points transfers current from the motherboard to the GPU. And each one is vitally important to the success of the Xbox even operating functionally. What happens though, under a full load, while the Xbox is most likely playing a game or watching a movie, the GPU heats up really hot, performing its billion instructions a second. And that causes a lot of stress on the joints under the GPU itself. In certain circumstances, the Xbox 360 heats up so much that it causes the GPU solder points to actually break apart from the board, and then they don't connect right when it's cooled down, thus leaving them apart from each other, and the Xbox cannot function after that point. Here is we actually can fix this problem simply by using a reflow station like this one. What happens is we need to melt the solder at 217 degrees Celsius so that the connections can get put back together per se. And to do that, we need to melt them all at once, because if the heat is not distributed across each point correctly, then there's going to be no way to fix the Xbox. Stop it for a second. So what we do here is we actually prepare the board to be reflown and then reflow it. We cover it with a heat-resistant sticky tin that will protect all the components in the motherboard besides what we were trying to get to. And then we simply just put it under. We set our reflow station to exactly what we need, and then we watch it go. So what you can see going on here is air is coming through the top. It's getting sucked through by a fan, and that passes through a heating element that's programmed by the user, and it's hitting the top of the chip. This is allowing it to flow evenly, the heat on the GPU, thus resoldering it to the board. The bottom is heated up so that the board doesn't warp during the process, and the tin on the outside is to prevent all the components, again, from breaking off the board because it gets so hot. You need a type of flux to lie under the chip so that when the solder reconnects, it'll connect fresh and it won't be a kind of a burnt solder which won't pass current good enough. Perfect. Here we have three different heat equations, our primary heat equations. The first one being conduction, the second one being convection, and the third one being radiation. For us, conduction is the most important, as this is what lets the heatsink take away the heat dissipated from the GPU and CPU itself. Our second would be convection, which has to do with the air surrounding the heat sinks and the whole Xbox itself. And unfortunately, we don't have much radiation coming from the Xbox, but that could be a good thing, I suppose. According to the laws of thermodynamics, heat is the transfer of one body or region to another through a thermal contact. For conduction, our equation right here, we can actually use a different one, which is Fourier's equation. Fourier's equation can be stated as the change of Q over the change small t equals negative K A d big T all over T. Where A is the cross-sectional area of the top of the CPU or GPU, in our case the GPU. Big DT is going to be the change in temperature from initial to final. And dx is the distance between the heatsink and the processor itself, which contains where the thermal flux will be located. Is the thermal conductivity constant found in the thermal paste we are using. Most time you keep it constant, but in reality it's quite the contrary. It's different throughout, as where in each part of the processor itself actually is a different temperature because it houses different elements that are needed during different operations. Okay. Here among this mess of words we have something called Newton's laws of cooling. Q is the thermal energy in joules, and this dq over dt would be the change in it. H, which is the heat transfer coefficient, lies right there. The surface area also comes into play, as well as all the temperatures of the object surface of the interior, the temperature of the environment on the outside, and the time-dependent thermal gradient between the environment and the objects, which is where the thermal paste comes. So what we normally do is we'll graph how hot a GPU gets by using a 2D graph. T would be the time constant, and temperature would be obviously temperature. So what we do is we would plot points of when the GPU starts to heat up under, we'll just say normal conditions here. Normal conditions. And what will happen is as soon as you turn it on, you'll start to see more of it heat up and kind of level off as it gets under a normal state. And under a full load, the graph would look similar, except what would happen is it would rise higher until it reaches a point at which it is under a full load, like the maximum temperature that the GPU can support, which would be actually higher than this, where this would equal out. So those graphs are good and all, but the truth be told, CPUs aren't linear. You can't graph them on a 2D plane. There exists a problem, and that lies in the aspect of it being 3D. They're in fact not homogeneous when it comes to temperature, although it appears it from the outside of the surface being homogeneous. So in order to counteract this, you actually need to do a 3D graph based on the X right here, a Y, and instead of a Z, it would have to be T for temperature. So what you can actually measure is, throughout the chip itself, what parts are heating up by this wave right here, this being the hotter part, this being the colder part, throughout the chip. Because when the thermal paste needs to pass the heat that goes from the top to the heatsink itself, we need to know what spots need the most support. And if we can level off these spots and make it somewhat constant throughout the whole thing, then our job is done, and we will have a stable system as opposed to the unstable system that exists today. That was fun. So truth be told, when examining both equations together, then plotting it on a 3D graph, we can get a better representation of what is actually going on top of the GPU when it displaces the heat out. And what we plan to do here is we plan to take Burgess' equation, figure out what we could apply to it to make it the best fit situation for our unstable system as of right now. So with the equations, you might be asking yourself, what lies ahead for us? Well, with the research that we're conducting right now and the ideas of airflow and mitigation of the convection within the Xbox, we can help make a better environment for this. In turn, we hope this research will promote other endeavors that are trying to cool off or make their system more stable.